Hello, everyone, and welcome to this lecture in the Hands on Large Language Models series. In the previous lecture, we started looking at an example in which we downloaded the Microsoft Phi 3 open source large language model from Hugging Face, and then we ran our first open source generative model on Google Colab. So, what we essentially did was we loaded the model from Hugging Face. We loaded the tokenizer automatically along with the model, and then we just gave a prompt such as assume that you are a stand-up comedian and create a funny joke about chickens. And we saw that the message was returned, or the new text was generated by the large language models. Why did the chicken join the band? Because it had the drumsticks. So what's the difference between this and ChatGPT? The major difference is that ChatGPT is closed source, which means that when we interact with ChatGPT, we cannot change too many things in the underlying code itself. We just have to pass the message and the response is received to us. The way ChatGPT operates, it's like a black box. But the difference here is that here it's like opening the black box. We are dealing with open source language models here. And with open source language models, you can download it on your laptop and run it on your laptop, or you can even run it on cloud, such as the Google Colab interface, which I'm showing to you right now. We can even go a step further and we can actually change the parameters within this model itself. So here we have loaded the pre-trained model, but we can even go ahead, change the number of transformer layers, change the number of attention heads which are present in each transformer block, change the learning rate. We can do all of these things with open source models. So in the previous lecture, we looked at how to interface these open source models with Google Colab and how to generate the next sentences, just like you do with ChatGPT. This is incredibly useful, this open source framework, because it opens the pathway for doing research for solving new problems. Because if you want to solve new LLM problems, do research, more often than not, you want to shine a torch on the black box, which is ChatGPT, and that's why dealing with open source language models is preferred. Throughout this lecture series, I'll be showing you closed source as well as open source models. Today's lecture is again extremely application oriented, which is the main purpose of this whole lecture series. And today we are going to look at one specific application, and that is text classification. We are going to use large language models for text classification. I'm going to divide this into a series of 2 to 3 lectures. In the first lecture, which is today, we are going to be using representative models for text classification. And in the next lecture, we will start looking at generative models for text classification. So within the representative type of models, also there are two types of categories, and within those categories, we are going to look at the first category today. So within the representation models, also you can do a task-specific representation model, or you can build an embedding and then run a model such as linear regression, etc., to do the final classification. Today we are going to look at a task-specific representation model. Okay. So in this figure, what I'm showing you is that language models can be used for text classification, and this application finds uses in a wide range of fields. So if you have a text and if you want to classify it in customer service, returns, or shipping category, you can do it with language models. If you are a inventor or if you're a designer of a social media network such as Facebook, and if you want to detect whether some text is hate speech or not, you can use a language model to flag the text as hate speech or not a hate speech. So again, text classification becomes very relevant here. If you are scrolling through the Instagram feed and if you want to take a piece of text and if you want to bucket it into a particular tagline, such as whether I will show this to the user or whether I will not show this to the user, then also text classification becomes very important. So there are a huge range of AI applications in which text classification plays a key role. And until now, you may have learnt of classification models in traditional machine learning, such as logistic regression, etc. Support vector machines, maybe. Neural networks are also used for classification. And we are just going to look at another section of classification models, and which are language models. Okay. And both types of language models can be used for classification. We can even do classification using generative models, such as GPT, and we can even do classification with representative models. Representative models are models such as BERT, RoBERTa, etc. It is a bit counterintuitive that we can do classification with generative models, but it is completely possible. So, for example, if you receive an input such as this, we'll need to train a generative model so that every input it receives, the output is something like this. The input class is of the type either returns or shipping or customer service. Whereas in representation language models, we can define the classes as 0, 1, and 2, and then the output would be a categorical output, such as 0 or 1 or 2. That's the main difference. Remember, generative models generate new text, right? So in this case, the text they generate is the input class is of this type. Whereas representation models can just directly output the category 0, 1, or 2. But both type of models can be used for text classification, GPT as well as BERT. In today's lecture, we are going to look at representative models for doing the text classification task. Okay, so let us get started with the application which we will look at in today's lecture. And the application is going to be movie review sentiment analysis. So let's say you have a IMDb, or you have something like Rotten Tomatoes, right? And now I want to build a system which takes in, or build a machine learning or a language model which looks at the particular review, and then let's say classifies it as good or not good, just based on the review. So, or put in another way, based on the review, I want to classify the review as, is it a positive review or is it going to be a negative review? In what cases would this be useful? Imagine if you are a company who is a film critic company, and you want to make a list of all of the movies which are good movies in the past 10 years. The simplest thing you can do is make a database of all of the movies in the past 10 years, run this language model, and then look at those movies which have been classified as with the good reviews. That's one of the simplest things you can do. And that's why this project which we are going to do today is going to be extremely relevant in cases such as this. Another thing which I would like to mention is that whatever code I will display today and run in front of you, the same code you can use for any other task. Currently, we are doing movie review sentiment analysis, right? You can do any other task with it, such as Twitter sentiment analysis, Facebook hate speech analysis, any kind of a classification task. Now, we decided that we wanted to use representation models, right? But within representation models, also there are two kinds of buckets. First is task specific models, and second is embedding type of models. Let me explain to you the difference between these two types. So, let's say we are using a representation model such as BERT. Now, if we go in the first category, which is the task specific, in the task specific model, the what we do is that the foundational model is taken and then it is fine tuned for a very specific task, such as perform classification or do translation or do text summarization, etc. Whereas if you take the second route of embeddings, the objective is just to create embeddings which are features. So let's say you have one sentence, and if you have sentences which you want to classify as hate speech or not, you will convert these sentences into higher dimensional feature spaces, and which are called as embeddings. And then you would apply some sort of let's say logistic regression, etc., to classify whether the it's hate speech or not hate speech. In our case, we take the we take the movie reviews, we convert each review into a higher dimensional feature space, and then we'll apply logistic regression or a classification neural network, and then classify whether the movie is a positive review or it's a negative review. That's basically embeddings. Fine tuning is directly when you give the input, the pre-trained model is fine-tuned to do this specific task. It's fine-tuned to look at, let's say, reviews and classify whether it's positive review or negative review. So then we don't have to train another or put another logistic regression or classification neural network layer if we go through this first category. In today's lecture, we are going to look at especially this first category, which is representation models. So we are going to look at representation models, and within representation models, we are going to look at task specific representation models. So we are going to look at models which are pre-trained using representation model settings such as only encoder only setting, and then they are trained on a specific task so that they can be good for our purpose, which is looking at movie reviews and classifying whether it's positive, neutral, or let's say the sentiment is negative of the review. So here also there are two options to do this. Either we can start with the BERT model, let's say, which is the foundational model, and let's say we can do the fine tuning ourselves. So we can do the fine tuning by uh, ourselves, which means that we'll need to take the foundational model and train it again on a specific data set and teach the model what is a good review, what is a bad review. So this fine tuning is done on a labeled data set. And the second type is we use pre-existing fine-tuned models. We use pre-existing fine-tuned models which someone else has already created for us. So in this lecture, what we are going to do is we are going to use the pre-existing fine-tuned models, which means that we will keep the models frozen. We will not be doing any fine-tuning ourselves. We will not be doing any training ourselves. So we will use pre-trained models which others have already fine-tuned for us. Where will we get these models? I'll show you that in a second, but we are going to get all of these models from Hugging Face. Now, whenever you're presented with a machine learning problem, you'll always have this dilemma that whether I should do the fine tuning or whether I should use an already fine tuned model. The best way to go about it is you first start using pre existing fine tuned models instead of uh, redefining or reinventing the wheel. And then, if the results are not good, then you can go ahead with fine tuning your own model, because this fine tuning your own model generally takes a bit of time. Okay, now what I want to do is that first, before we go to model selection, I first want to show you the data set which we are going to be using. So here's the data set. It's from a website called Rotten Tomatoes. And Rotten Tomatoes, essentially, you can go ahead to Rotten Tomatoes and you can see that it's a website where we have movies and then we have the reviews corresponding to every movie. So it's a big list where there are movies and there are reviews associated with every movie. Now on Hugging Face, there are huge amount of data sets, right? And one such data sets is the movie review data from Rotten Tomatoes. We are going to use this data set and let's look at it a bit. The training data has 8,000 rows, which is reviews for 8,000 movies. And you can see that each movie is uh, uh, a description. And the let's see, the test data has around 1,000 rows and the validation data has 1,000 rows. So overall, it seems that the data set as a whole is about 10,000 movies, which looks like a big enough data set. And we are going to use this data set in our code. So let us get ahead with coding right now. As I mentioned, I'm following this book, Hands on Large Language Models by Jay Alamar. It was just released last month, and the code which we are using now is written in this book. So I'll go through this code and I'll try to explain it step by step. First step before we get started is we want to install all of these packages. For today's code, we'll need the datasets package, which is given by Hugging Face, and we will need the transformers package, which is also given by Hugging Face. So you can do pip install and you can install these two packages. The remaining two packages we'll need in subsequent lectures. So if you want to, you can go ahead and run this full command and install all of the packages right now itself so that you can use them for later lectures as well. Once the packages are installed, the next thing which you have to do is you have to load the dataset. So datasets from datasets. So this is a package which will help you load datasets from Hugging Face. So when you do load dataset Rotten Tomatoes, it will automatically download this particular dataset from Hugging Face itself. And when you download this dataset, you can print out the data and you'll see that it contains training 8530, validation 1066, and testing 1066. This is exactly the data set which you saw over here, right? 8530, 1066, and 1066. It's rounded off to 1.07k, which is 1070. This is the exact same data set. All right, so we have downloaded the data set right now, and let us see some elements. So here what I'm doing is that I'm looking at the training data set and I'm printing the first element of the training data and the last element of the training data. So here you can see that this is the text review from the first element and this is the review from the last element. If you read the review, you will see that the first review is good actually. It says that the movie is going to make a splash even greater than Arnold Schwarzenegger movie. With the second movie, it's written things get really weird, though not particularly scary. The movie does not have any content. So the first movie review has a positive sentiment associated with it, and the second review has a negative sentiment, right? So look at the labels. The first movie has the label 1, which is a positive sentiment, and the second movie has a label 0, which means that it has a negative sentiment. So look at the way this data is structured itself. Within the training data, the data set has two features. It has the text, which is the movie review description, and it has the label. And the label format is either it can be 1 or it can be 0. 1 means that it's a positive review, and 0 means that it's a negative review. When you load the data set, it's always very important to understand the format of the data itself. And that becomes very important because otherwise you feel a bit disconnected with the data. Right. So I always emphasize a lot on the data cleaning, data visualization, and data manipulation part before moving to the modeling itself. So now we have generated the data. Now the next task for us is to use the representation model itself. So as we decided, we are going to use a pre-existing fine-tuned model, and on top of that, we are going to use a representation model which is fine-tuned on a specific data already fine-tuned. Now, one thing which I would like to mention is that model selection is not an easy task. And the reason is because Hugging Face itself has more than 60,000 models for text classification, and it has more than 8,000 models that generate embeddings. So, embeddings is the second category which I mentioned over here. We don't want to look at that category right now. We only want to look at this first category. But here also there are 60,000 plus models for text classification. Which one do we typically use? So the fundamental rule here is that you always start with BERT like models, which are very good and very robust. So here is a timeline in which different BERT models were invented. BERT, the original BERT came just before 2019. Then came RoBERTa, which is extremely famous. Then came Albert, Distilbert, and DiBERTa. DiBERTa is the latest one which came in 2020 mid. After that, also number of models have come out, but these are the original models which are usually very good. So, as a thumb rule, the good starting points are either of these six models. So, BERT model, RoBERTa base model, Distilbert base model, DiBERTa base model, all of what we have shown here, BERT Tiny and Albert base V2. Among this, I usually start with either the BERT base model or the RoBERTa base model. And you can find these on Hugging Face. So, let me show you now. Uh, yeah, so this is the RoBERTa base model which is present on Hugging Face, and you can start with these models, but remember that this model is not fine tuned on a specific data set. This model is pre-trained on a large corpus of English data. It's not fine tuned on a data set which consists reviews. So we need a model which is not only pre-trained but also it's fine tuned. So here we will try to look for models which is based on either of these fundamental models. The reason they are called base models is they're pre-trained foundational models. They are not fine-tuned necessarily. So I am looking for a model which is fine-tuned on top of these base models. One such very good model is this Twitter RoBERTa based sentiment latest. You can see from the downloads, the last month itself, there are around 2 million downloads for this model, and that's a good sign that this is a pretty decent and popular model. So here you can see that this is a RoBERTa based model and it is fine tuned for sentiment analysis. That's awesome. But it's fine tuned with Twitter tweets. That's not exactly what we needed, right? We wanted a model which is fine tuned on movie data. But we are going to go ahead with this because whether it's tweets or whether it's movie data reviews, if a model has learned to understand the sentiment behind sentences, if this model is trained on 124 million tweets, the model is hopefully good at looking at sentences and identifying the sentiment behind sentences, whether it's positive or whether it's negative, right? All right. So this is the model which we are going to use. It's called as Twitter RoBERTa base sentiment latest. Again, when you use a model, don't blindly copy paste this. Try to look at the reference paper behind each model. usually there is a reference paper in which that model is explained. So here you can see that this reference paper is diachronic language models from Twitter. So you can go ahead and search the number of citations also. So here you can see this cited 250 times, which means it's a very decent paper. And here you see that here the model was described and it was invented or released in 2020. Because this was again later, or I think this was released in 2022, I guess. Yeah, it was released in 2022. So let's go ahead and use this model right now. Okay, so as I've mentioned here, we choose the Twitter RoBERTa base model for sentiment analysis, and let's see how well it does for movie reviews. All right. So, okay, my next step is we are going to use a task specific model, and when I say task specific, it involves fine tuning. So we are using this Twitter RoBERTa based sentiment latest, and you just have to give the model path to the Hugging Face model. So here you can see that from here you can get the model path, and then you have to mention this model path over here. And as we discussed in the last lecture, whenever you are dealing with language models, it's good to create a pipeline. In this pipeline, you mention the model path, you mention the tokenizer. Now here you see the model and tokenizer both have been mentioned as model paths, which means that when you do this, the tokenizer will be set as by default to whatever tokenizer was used when this model was constructed. And I have given a schematic of the tokenizer here. So the tokenizer is a subword tokenizer, which means that one word is not necessarily one token, but sometimes even subwords can be token. So what happens is that whenever you get a movie review, so let's say you get a movie review, it's broken down into these tokens, and then these tokens are then fed into a transformer. These tokens are fed into a transformer, and then we have the final we have the fine tuning process. We have the fine tuning process on the output from the transformer, and after this fine tuning process, then the output is that whether the review is positive or whether the review is negative. So for us, this part is already taken care of by the people who have developed this model. All we have to do in this code is that we have to essentially load the movies data set. We have to pass that data set into this model. We have to pass that data set into this model, and we have to do the prediction. And after doing the prediction, we have to do the evaluation, which is basically understanding whether the model is performing well or not. Right. So this is the pipeline. We have the model, we have the subword tokenizer, and then let me just go ahead and run this. So when you go ahead and run this model, you'll see that it does take some time, but it's not huge. So it's basically 501 megabytes for this model to download. So based on the internet speed, it might take around 5 to 6 minutes for you to download this model on your laptop. Once the model is downloaded, our next step, as I mentioned on this whiteboard, is to pass the movie's data into this model itself. So that's going to be our next step and generate the predictions. So here, if you see, this is that code in which we pass the data which we have downloaded. So here you can see that we have downloaded the movie's data. Oops, over here, yeah, we have downloaded the movie's data. We have to pass it into the model pipeline. Let's see how this data is passed into the model pipeline. So first is PQDM, which is basically a progress meter for how much predictions have been done. And then here you see pipe, and pipe is basically this pipeline. So we have to pass the data into this pipeline, right? Now here you see key data set is the module which is offered by Hugging Face transformers, and it lets you access specific keys of the data. So we are what we are essentially saying over here is that we are looking at this data set, and we are looking at the testing data especially. So here you see we are looking at the data test, which means that we are looking at the testing data, since the prediction has to be done on the test data, not on the training data, right? So we are looking at the test data, and we are going to access the keys corresponding to text. So here you see that the test data has two keys. The test data has keys which are named as text and label. So we don't need to pass in the labels initially, right? The labels are the predictions. We need to pass in the text, which is the reviews. and then we need to run the model on the reviews. So what this code does is that it looks at the particular key, so it keys the data set with whatever is mentioned here. So key data set has two arguments. First you mention the data, and then you mention the key which you want to look into. So I'm going to look at the key text, which means that we'll look at the reviews itself, and then the length is the total length of the testing data set, right? Okay, so I'm going to pass my data set into this pipeline, and then I'll get an output. Now, one thing which I want to show over here is that when you pass a data into this model, the output is you get three numbers as the output. You get a number for the negative score, you get a number for the positive score, and you get a number for the neutral, and you get a number for positive, and all of these add up to one. So then we are going to only look at the negative and positive, and we are going to choose that index which has the highest value. So if in this case the negative is much higher than the positive, right? So this review will be classified as negative review. All right. So here what we are going to do is that we are going to look at the output, and we are going to look at output 0 score, which means that we are going to look at the negative score, because the negative is indexed as 0. If you see over here, the negative is indexed as 0, positive neutral is 1, and positive is indexed as 2. I think that would also be written as somewhere here. Yeah. So negative is indexed as 0, neutral is indexed as 1, and positive is indexed as 2. All right. So we are going to look at the negative score, we are going to look at the positive score, and then the output from that particular movie review is that index which has the maximum value. So we are going to compare the negative and the positive score. If the negative score has a higher value, then the output will be index 0. If the positive score is will have the highest value, then the output will be index 1. So 0 means that the sentiment is negative, and 1 means that the sentiment is positive. And we are going to do this for all the movies in our testing data set. So see, we are running a loop here. So we are looking at each movie review step by step. We are going to look at the first movie, then we are going to look at the second movie, then we are going to look at the third movie, etc. So we'll follow the uh, entries in the movies step by step, and then for each entry we are going to find whether it's corresponding to 0, which means negative score, which means negative sentiment, or 1, which is positive sentiment. And then we get this ypred, which is the prediction matrix for, or rather the prediction list for all the reviews. So if you look at ypred, it will consist of a huge bunch of numbers around 1066, because that's the testing data. So if you print ypred of 0, which means that the prediction for the first movie in the testing data set, so that will be 1. Similar, so that means that this movie is classified as positive. Similarly, you can run the prediction for different indices in the data set itself, right? All right, now once we have done the prediction, yeah, so see, ypred 0 is equal to 1. Similarly, we can run ypred 50, which is the prediction for the 50th movie in the testing data set. That is 0, which means that the 50th movie, the sentiment is negative. Once we have done the entire prediction, the next step for us is going to be evaluation. So now we have got this prediction where we have a list which consists of answers, whether the answers are whether the movie is classified as a positive sentiment movie, or whether the movie is classified as negative sentiment movie. In the next step, what we have to do is that we have to construct the classification report, which means that we have to evaluate whether the performance of our NLP model is good or not. And for that, we are going to look at something which is called as the confusion matrix. For such binary classification tasks, confusion matrix is one of the best way to evaluate whether our classifier is doing a good job or not. The confusion matrix essentially has four columns: true positives, which means that the positive review is correctly identified as positive; true negative, which means that the negative review is correctly identified as negative; false positive, which means that the negative review is incorrectly identified as positive; and false negative, which means that the positive review is incorrectly identified as negative. Now, based on these four values, there are these four metrics which are constructed. The first metric is called as precision. So that is true positives divided by true positives plus false negatives. So plus false positives. So this essentially gives us an indication that of all the positives, how many of them are actual true positives and how many are wrongly classified as positives, and we want this value to be as high as possible. This is called as precision. The second is recall. The only difference in precision and recall is that in recall there is a false negative term in the denominator, which means that values which are actually positive but falsely classified as negative. This is an indication that among all the positives, how many of us are we able to capture? And we also want these values to be as high as possible. We want the precision and the recall values for the negative review as well as the positive review to be as high as possible. Instead of looking at these two values separately, one composite value which researchers or ML engineers generally look at is called as the F1 score. The F1 score is 2 into precision into recall divided by precision plus recall. And this value also needs to be as high as possible. There is no particular value which I can say that okay, F1 score needs to be higher than zero point 0.8, F1 score needs to be higher than zero point 0.9. It depends on problem to problem. But as a baseline, if we get an F1 score of about zero point 0.8, it means generally our model is doing a good job. Then there is something which is called a support. This means that how many of our samples are in the positive class and how many are in the negative class. So if it's ideal that we have 50% in the positive and 50% in the negative, otherwise it leads to an imbalanced data set. So generally, having an imbalanced data set is not very favorable for us, because then our metrics might be skewed towards that data which has, so let's say positive, if we have reviews which are 80% positive, the true data itself, or only 20% are negative, that's not generally good. But in our case, this data set is good because in the testing data, we have 533 whose actual value is positive and 533 whose actual value is negative. So this is the F1 score, and the last score is the accuracy, which means basically that how many we actually got correct. This is the simplest one to understand. Out of all the predictions, how many did we get correct? So that is true positive plus true negative divided by true positive plus true negative plus false positive plus false negative. That is the accuracy score. So now what I'm going to do is that scikit-learn essentially provides a function which is called as classification report, and you, in the classification report, you have to pass in the true values. So the y true is basically the um, underlying true data set. Let me show you where we have defined y true. Yeah, so y true is just going to be the label in the underlying data. So if you see, the data itself has a feature which is called as label, that is going to be the true values, and y prediction is going to be the y underscore pred, which we have already yeah, where is it? Yeah, y underscore pred is something which we have already computed over here. So then to generate the classification report, in this function we have to give two entries, y true and y prediction, and we also have to give the target names, negative review and positive review. So here you see, ultimately we have to generate the matrix such as this. So here I have shown negative review and positive review, right? Because precision and recall are calculated separately for the negative and positive review. Similarly for F1. F1 score is calculated separately for negative and positive reviews. Accuracy is just one score for all. So if you run this and if you print the performance, you will see that this is the performance sheet. The first thing I usually look at is the support. So here we can see that we have 533 examples whose true value is positive sentiment and 533 whose true value is negative sentiment, which is good. This means that my data set, my testing data set is balanced. Then I look at the accuracy because it's the easiest to understand. The accuracy is zero point 0.8, which means out of the 1066 testing data set, 80%, my classifier is doing a good job on 80% of the data, which means for 80% of the testing data, my representation model is doing a good job, is classifying correctly. That's actually awesome, right? If you think about it, we used a pre-trained and fine-tuned model on a Twitter data set. So this model is actually fine-tuned on this model is actually fine-tuned on Twitter data, and we have tested it or trained it or done the predictions on the movie data set, and on this data set itself the model is doing a good job, which this comes under the category of transfer learning a bit, where you train on some random separate data set. So like here we have trained on the Twitter data set, but we are even on the movie data set, the model is doing a good performance. 80% is a decent and a good job, I think. That is because whether it's Twitter data or movie data, the model has learned to understand sentiments behind sentences because it's trained on 124 million tweets. So it's actually a very smart model which can look at a sentence and classify it as a positive sentence or a negative sentiment. The second metric I look at is the F1 score. This is 0.88, which 0.8, which is good. Generally, as I mentioned, as a baseline, an F1 score of 0.8 is good, and the F1 score for negative and the positive should not be too different. That's also good. Our F1 score for positive reviews and negative reviews are very close to each other, and both are zero point 0.8. That's awesome. Then I'll start looking at individual metrics. So from the recall metric, I can see that the model generally identifies negative reviews much better than positive reviews. So as a scope for improvement, we can maybe try to improve the model and its capabilities for detecting positive reviews. On the precision, it's reverse. So the model is good at essentially preventing errors and having fewer number of false positives than it has than it has false negatives. So if you look at the precision has false positives. So higher precision value means that the model has fewer number of false positives in the case of positive reviews than in the case of negative reviews. So in the case of negative reviews, sometimes positive are also classified as negative, and that's not good. So improving the precision and recall values might be a scope for further improvement in this model. But overall, as a whole, the model generally does a good job because the accuracy is zero point 0.8 and the F1 score for both negative and positive reviews is close to zero point 0.8. So I'm very happy with the model performance, especially considering that it's trained on a completely different data, which is the Twitter data. Awesome. So this brings us to the end of this lecture where we used a representation model which is pre-trained and which is fine-tuned on Twitter dataset. And then we use this model to predict the movie review sentiments for the movie review dataset. So here's the movie review dataset from Rotten Tomatoes we downloaded from Hugging Face. And then we used a pre-trained plus fine-tuned model to classify this dataset itself into whether it's a positive movie or whether it's a positive review or whether it's a negative review. And we saw that in just few lines of code. Here you see I've just written 5 to 6 lines of code, right? And we implemented a very functional model in just 5 to 6 lines of code using the power of Hugging Face and using the power of Google Colab. In the next lecture, what we are going to look at is we are going to look at the second type of representation models, which is embeddings. Until now, we looked at the first type of representation model, which is for classification, or I should call it fine tuning on a task specific data. So it is a task specific model. In the next lecture, we'll look at embedding model. And in the lecture after that, we'll look at using generative language models for text classification. So we'll have 3 lectures on text classification using large language models. I hope all of you are liking this hands-on aspect which I'm introducing in this lecture series. The previous lecture series, Build LLMs from Scratch, was theoretical. It's completely fundamental and foundational. That's highly relevant. And as you're getting introduced to the fundamental aspect, what's also important is to teach you the applications. And that's why we have come up with this series. Thank you so much, everyone. And I look forward to seeing you in the next lecture.